Hello, everyone, and welcome to today's webinar, Avalanche Photodiodes, Design and Applications, presented by OSI Optoelectronics and hosted by Photonics Media. My name is Sarah Weiler, and I'm the Photonics Media Webinar Coordinator. I would like to introduce today's presenter, Dr. Olex Gusha, Lead Scientist for Semiconductor Devices at OSI. Gusha will be speaking today in depth on Avalanche Photodiodes, or APDs. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording will be available on the Photonics Media website shortly after today's presentation. Everybody will receive a link to that recording, so if you know someone who couldn't be here today, please let them know the recording will be online. We encourage you to ask questions at any time during the presentation. Just type your question into the questions box to the right of your screen, and our presenter will respond to as many as possible at the close of the presentation. And with nothing further, I would like to introduce our speaker, Dr. Olex Gusha. Welcome, Olex. We see your screen.
Okay, hello everyone. And first of all, I would like to thank the organizers for this webinar and for the opportunity to make presentation. And the presentation, as was told about, is about Avalanche Photodiodes, their design, function, properties, and some applications. The scope of the webinar does not allow to discuss everything in detail, but we will cover the most important, to my mind, topics related to Avalanche Photodiodes. We will start with a brief description of Avalanche Photodiodes, the application and basics of operation, then proceed with the description of important parameters, traditional structures, structure function properties and parameters characterization, and we will conclude with the description of Geiger mode APDs and silicon photomultipliers. Avalanche photodiodes are the semiconductor devices that designed to operate under specific conditions. APDs have similar structures to regular pin photodiodes. The design features include a moderately doped region, which called the Avalanche region, allowing carriers multiplication at an appropriate bias. Due to avalanche multiplication of carriers created through light absorption, APDs allow detection of very low intensity optical signals and very fast response time. Currently available APDs include structures with active area diameters from tens of micrometers to over 10 millimeters. In some ways, APDs can be considered as an alternative to the photomultiplier tubes. They have advantages of operating at lower bias and smaller size, but the drawback is lower dynamic range. Important features of APDs is their high reliability at various environmental conditions. Avalanche photodiodes have found lots of applications in scientific research and various industries, which includes semiconductor fabrication equipment, laser scanners, medical imaging, molecular imaging, high-energy physics, analytical instrumentations, and most recently, LiDARs, rangefinders, and of course, optical communication. Avalanche multiplication is and its use of to enhance the photodiode signal was known from late 50s. Assume that we have a slab of silicon uniformly doped with a p-type dopant and applied anode and cathode doping on the slab's side. Applying the reverse bias across the slab, the electric field is created. Non-equilibrium carriers generated through light absorption will be accelerated in the field, and the higher the field, the higher the energy and momentum each carrier acquires. Drifting carriers may encounter collisions with the dopant atoms, and if the carrier energy is high enough, it can ionize the dopant atom, creating additional free carriers through the process called impact ionization. The avalanche multiplication starts when the electric field across the semiconductor bulk reaches the critical value, and the higher the electric field, the larger the avalanche. The electric field is unique for each semiconductor material, as well as the impact ionization coefficients for electrons and holes. The ionization coefficients alpha for electron and beta for holes depend on the electric field strengths, as well as the ratio K. Dependently on semiconductor material, either electrons or holes or both types of carriers can create the avalanche. The example on this slide is where the avalanche is started by the electron impact ionization. Among the most important parameters of any APD are avalanche gain or multiplication factor, noise, operating bias, temperature dependence of parameters, response time, and gain bandwidth. Dependently on the required performance, one can select the optimal APD structure. For any APD structure, the avalanche gain and noise depend on many parameters, and it is not easy to analyze them theoretically. However, using reasonable assumptions, the analysis can be simplified significantly, and one of the important assumptions is that all non-equilibrium carriers are equal and participate in avalanche multiplication equally. Moving forward in our presentation, let's discuss APD parameters, and let's start with the avalanche gain. Assuming position-independent equal ionization coefficients for electrons and holes, where all the carriers creating the avalanche are equal, the avalanche gain over the depleted thickness of semiconductor for carriers injected at its edge can be approximated with the simple equation. If the ionization coefficients cannot be considered as equal, the avalanche gain over the depleted thickness gets a more complicated expression. Fortunately, it is very easy to measure the avalanche gain experimentally, and we will discuss it later in this presentation. Next, we'll move and discuss noise in avalanche photodiodes. Using Poisson statistics for the shot noise, which is the most main contributor to the noise current for any pin photodiode and APD, and assuming that the gain is the same for any event at selected bias, the shot noise current density of APD is given with this simple equation. The assumption of equal gain for all carriers means that compared to a regular pin photodiode, such an ideal APD should be able to provide the output signal with m times higher amplitude than the primary signal from a pin photodiode, and with basically the same signal-to-noise ratio as for a pin photodiode of the same size. This would be an excellent result. But the real life is not that simple. The assumption of equal gain M for each carrier is actually not correct. As was shown by McIntyre and later developed by Campbell's group, the probability to create an avalanche is widely distributed. This is demonstrated by the graph to the right, where the probability of 10 initially identical electrons to create an avalanche is shown for different values of avalanche gain and for two different values of K. As we see, the probability is well below unity for any gain. This creates large additional noise in APD, which can make the device not practical at all. Considering effects of gain non-uniformity, the equation for the noise current density must be rewritten for the average values. McIntyre introduced the factor F that describes an increase in the noise value due to the gain non-uniformity. Then substituting m² average with the theoretical values, we obtain correct expression for the average noise current. In this expression, m is the average gain discussed previously, and F is the excess noise factor introduced by McIntyre. It is clear from this expression that to improve APD performance, the excess noise factor must be as small as possible. Ideally, it should be 1. And this is the main requirement for good APD, for a good APD. How to make the excess noise factor smaller? Obviously, wide distribution of carriers over their efficiency to create an avalanche produces large excess noise, leading to a very large value of the excess noise factor F. To reduce the F factor value, the distribution width of the gain probability for carriers has to be made narrower. This can be achieved using the following approaches. First, choosing the structure in which only one carrier type participates in multiplication. This creates twice narrower distribution and hence smaller excess noise factor. Second option, thinner multiplication region may create narrower distribution of the gain and hence lower F factor value. Third, there is a higher uniformity of doping in the multiplication region, also makes the distribution narrower and reduces the excess noise factor value. And of course, the last, lower operating bias reduces F factor value as well. We will discuss some of these approaches later during this presentation. So let's talk about basic structures of APDs. One of the main requirements for any structure is to support high electric field to achieve the avalanche effect. Let's discuss first the so-called reach-through structures. These are the structures that operate under a complete depletion of the whole thickness of the semiconductor active region, and the necessary critical electric field is supported by heavily doped anode and cathode. Consider a slab of lightly doped p-type silicon with heavily doped anode on the bottom and cathode on the top. Theoretically, we can apply reverse bias, and at a certain bias value, the electric field might reach its critical value. However, as everybody knows, the structure shown in this image will never support high electric field since an early breakdown will occur at the edges of the chip. We must create the guard rings and edge channel stoppers to avoid early breakdown and support high electric field across the whole thickness of the die. Moreover, to improve uniformity of the avalanche multiplication, it is to our advantage to create a dedicated avalanche multiplication layer called sometimes P-well with a moderate dopant concentration P+. Then, upon reverse biasing, the electric field will reach its critical value only within a thin layer P+, and avalanche multiplication conditions will be satisfied only within this layer. The edge dark current will not be subject to avalanche multiplication. This structure can support high bias necessary to reach high gain. Next, we'll discuss the so-called bevel edge terminated APD structures, in which the avalanche region P+ is a part of the epi structure. To support high electric field, we can modify the die by beveling edges. Beveling allows to distribute electric field lines in the way that their density at the edges of the die is much lower than in the middle. It means that upon reverse biasing of the die, the electric field will reach its critical value in the middle portion of the die, but never at the edges. As a result, the avalanche multiplication will proceed uniformly everywhere except the edges, and the dark current generated at the edges of the die will not participate in multiplication. Such approach improves greatly the uniformity of the avalanche process. Now, after we discussed the basic APD structures, we can return to the approaches to improve the excess noise of APDs. Among the well-known options is to reduce the F factor by designing the structures that allow only one type of carrier to participate in multiplication. Such design may employ the so-called separate absorption and charge multiplication regions used in compound semiconductors and germanium silicon APDs. The other option is creating narrower, more uniform multiplication region. This could be achieved by using thin epi layers and buried multiplication layers in silicon, germanium, and compound semiconductors. And also adding certain critical elements will further improve the gain uniformity. Let's consider a few examples. The image to the left shows schematically InGaAs APD structure in which the p-type absorption region is close to the light entry site. All light quanta are absorbed in this region, and then generated non-equilibrium carriers, electrons, are swept by electric field towards the multiplication region at the bottom of the structure, creating an avalanche. The non-equilibrium holes drift toward the anode on the top and do not participate in avalanche multiplication. Whereas typical values of the excess noise factor for in-gas APDs is about 10, some recently reported structures showed the value of a factor around 3 with the avalanche gain of around 40. The image to the right shows schematically germanium-silicon APD structure in which the germanium absorption layer is close to the light entry site. Illuminating the structure with infrared light, all light quanta will be absorbed in this absorption germanium layer. Generated non-equilibrium electrons will be swept by the electric field toward the silicon multiplication region at the bottom of the structure, creating the avalanche. Silicon is characterized by better ionization coefficients for electrons than germanium, which makes silicon a preferred multiplication layer. The non-equilibrium holes drift towards the anode on the top and do not participate in avalanche multiplication. Typical values for the excess noise factor achieved for germanium silicon APDs is around 3 with the avalanche gain of about 30. The other method to improve F factor is creating narrower and more uniform multiplication region, which produces narrower gain distribution and hence lower F factor values. This is achieved by using thin epi layers and deep implanted or buried multiplication layers in silicon, germanium, and compound semiconductors. As an example of silicon devices, a buried multiplication layer P+ can be created underneath the front side cathode with a small spacing. This allows to exclude certain surface dark currents from multiplication and to create more uniform electric field within the avalanche layer. Applying reverse bias and eliminating the diode, non-equilibrium electrons will participate in the avalanche process within the multiplication layer. Typical F factor values achieved for such structures are within the range from 2 to 10 at the gain value of about 100 for silicon at room temperature. Let's consider one more example of how adding certain structural elements allows to reduce F factor value. We will proceed with the bevel edge terminated large active area silicon APDs. This image shows schematically a silicon large area APD structure with a top P++ contact. The P+ multiplication epi layer is fully depleted under reverse bias. The N-type substrate is not necessarily fully depleted. The P+ contact ring on the top provides necessary support for beveling and serves as a top contact. The structure operates at the reverse bias between 1700 and 2100 volts with the gain of over 300 at room temperature and over 400 at 0 Celsius. The structure allows to produce APDs with the industry lowest A factor values. The spectral sensitivity ranges from vacuum UV to 1000 nanometers. Typical performance parameters achieved for such structures are: the excess noise factor is less than 1.3 for the gain of 300 at room temperature. Noise current spectral density per square millimeter active area is below 2e-14 amps per square root from Hertz at room temperature, which is more than 10 times better than for any other APD. Next, we'll discuss some most important performance parameters of APD. We will start with the APD gain. Consider as an example a silicon APD structure shown in the image. This is a front illuminated APD with a buried avalanche layer, and the dark and light current voltage characteristics are shown in the graph to the right. It's here, right? Gain at bias V is defined from the equation below as the difference between the photocurrent and dark current at the operating bias V. Where is my mouse? It's here, it's at this point, divided by the difference between the photocurrent and dark current at unity gain. The quantum efficiency measured at unity gain for the same structure is shown in the graph to the left. Obviously, this structure was optimized for the wavelength range around 800 nanometers. The gain dependence on the reverse bias at 800 nanometers was obtained using the methods that we just described, and it's shown on this graph to the right. The gain stays at unity up to approximately 40 volts and then starts rising. The graph shows slightly pronounced kink around 45 volts. It's here. It is interesting to compare the graph with the capacitance behavior with voltage. The graph for capacitance dependence on bias exhibits a slow decrease. It's here, slow decrease with bias up to the bias of approximately 45 volts due to depletion edge propagating through the P plus multiplication layer. At around 45 volts, the whole thickness of the multiplication layer is depleted, which is signaled by the beginning of a sharp drop in the capacitance value and a kink in the gain plot around 45 volts bias. Further increase in the applied bias leads to a fast propagation of a depletion edge through the P layer. This is evidenced by the capacitance saturation at around 60 volts bias, and rising bias further beyond 60 volts causes the electric field within the avalanche region to increase dramatically, creating a steadily increasing avalanche gain at 800 nanometers. Interestingly, the gain behavior at other wavelengths is different from the gain at 800 nanometers. At long wavelengths, the gain is high, but the quantum efficiency is very low, which is shown on the graph, quantum efficiency graph at the top left corner of this slide. And the overall sensitivity will be low. At short wavelengths, the gain is very low because the absorption edge, the absorption depth does not reach the buried multiplication layer, and only holes and just a small portion of electrons created by light absorption participate in the avalanche process. And we know that the impact ionization rate for holes in silicon is much lower than for electrons. Next, we will discuss the design allowing to improve UV sensitivity of avalanche photodiodes. One of the ways to improve UV sensitivity of silicon APDs is to build them using a back-illuminated structure. This figure shows a basic back-illuminated structure of APD. The N+ cathode is placed now at the bottom of the absorption P layer. The P+ anode is on the top of the structure. The P-doped multiplication layer is placed at the bottom next to the PN junction. The interconnect layer allows bringing all contacts on the top surface of the structure. Under illumination, the UV light is fully absorbed close to the top surface, and non-equilibrium carriers start drifting towards respective electrodes. Electrons, when reaching the multiplication layer, have enough energy to start the impact ionization, creating the avalanche. The quantum efficiency in this short wavelength spectral range is greatly improved now for the back-illuminated structure, and the gain for the short wavelength range becomes much higher, reaching the values characteristic for the front illuminated structure in the long wavelength spectral range. Let's now spend a few minutes showing how to estimate the excess noise factor for APD. This is probably one of the most difficult parameters to determine. In fact, each design of APD may require a unique approach, and it may become more like an art rather than science and technology to determine the F factor value. The noise spectral density for APD is determined primarily by the shot noise obeying the Poisson distribution. In practice, the dark current conditions are used to estimate the excess noise factor using the following equation. The figure shows parameters required to estimate the F factor. They include the light and dark currents at both the unity gain and the gain of interest. Only bulk portion of the dark current is going to be multiplied in the avalanche region. The surface dark current is not multiplied. In many cases, we can assume that the surface dark current does not depend on the applied bias. in which case the estimation of the F factor will be greatly simplified. To estimate the F factor value, we need to measure duct noise current spectral density at the bias of interest using a spectrum analyzer or lock-in amplifier. Then, assuming that all low bias value, that at low bias value, the duct current is primarily due to the surface current, and assuming that the surface duct current does not change with bias, we have to estimate the dark bulk current from the test data shown on the graph. And then using the light and dark current values from the graph, calculate the gain at each bias of interest. And finally, using two equations shown on this slide, calculate the excess noise factor value at the applied reverse bias V. As I mentioned, the assumption of the surface duct current being independent on the bias may not be valid. In this case, one needs to apply equations shown in this slide for each bias value separately and to solve the system of equations, finding the best fit for the values of the F factor for each bias. This may not be an easy task to do, of course. One of the important parameters of APDs is the gain dependence on temperature. This dependence is critical in many applications, since a small change in temperature may cause dramatic change in the gain value. Two factors influence the temperature dependence of gain. One is the semiconductor's band gap shift with temperature. For silicon, this shift becomes pronounced for the wavelength range above approximately 850 to 900 nanometers. As it is shown on the graph, the quantum efficiency becomes lower with temperature decrease for the wavelength range above 850 nanometers due to a drop in the absorption coefficient value caused by the band gap shift. However, the second factor that influences the temperature dependence of the avalanche gain is even more important. With temperature increase, drifting carriers have higher probability to collide with the host atoms, losing their energy to phonons, to heat actually. This shifts the avalanche onset to higher voltages, increasing the breakdown voltage and reducing thereby the gain at a given reverse bias. Figure to the right is a typical example of a dramatic change of the avalanche gain with temperature for a front-illuminated silicon APD with a buried multiplication layer. Typical values for the breakdown voltage temperature coefficient for silicon APDs are close to 1 volt per centigrade. For the best available commercial APDs, this coefficient is slightly below 0.7 volts per centigrade. Obviously, for the application in which the avalanche gain stability is important, the temperature stabilization has to be applied. Well, we discussed so far the avalanche photodiodes working in the analog linear mode, when the output current is proportional to the impinging light intensity. However, APDs may work in another type of application when incoming photons create an avalanche with the gain of 10 to the power 6 or higher, which allows digital counting of incoming photons. This regime of APD operation is called the Geiger mode, or single photon avalanche detector. Many APD structures allow using the same APD in either the analog or Geiger mode of operation. SPAD functions similarly to an analog APD, but the structure may be optimized to sustain high internal amplification, allowing detection of the lowest light fluxes, and low duct current, allowing to improve the detection efficiency. An example of an APD structure for the Geiger mode operation is shown on this slide to the right. The structure may feature very thin avalanche layer. The main idea of a Geiger mode APD is to bring its operation point above the breakdown voltage, which may allow the gain to exceed 10 to the power 6. This can be achieved only and only with the structures having very low duct current noise level. The decrease to decrease the dark noise counts, one can minimize the active area size and decrease the operation temperature. For example, down to 0 using thermoelectric coolers. Let's assume that we created a structure with a very low dark current. Then we need to arm the device with an excess bias, shown, for example, here with an excess bias. As shown in this image, the excess bias can be a few volts in magnitude. This is enough to create an avalanche with the gain of more than 1 million on each incoming photon. As a result, the spike of the output current may reach a few picoamps in amplitude, which can be counted by the downstream electronics. The avalanche must be quenched immediately after it reaches the maximum, otherwise the device will be burned out. We will discuss quenching on the next slide. The dark carriers also create an avalanche with the same amplitude of the output spike, and the goal of the designers is to minimize the dark current rate. The main performance parameters relevant for Geiger mode APDs are photon detection efficiency, dark current rate, timing resolution, and after pulsing probability, which is a false avalanche due to charge trapping releasing, carrier tunneling, and intravalley optical transitions. The excess noise factor is not relevant for Geiger mode APDs. And note also that the photon detection efficiency increases with the excess noise voltage, and the fundamental spot trade-off is dark current rate and photon detection efficiency, both increase with bias. Well, Geiger mode APDs can only function if an effective avalanche quenching is provided. The simplest way to quench the avalanche is to add a quenching resistor in series with spot. In this case, after starting the avalanche, the resistance of the diode drops dramatically, and the current flow through the quenching resistor causes a voltage drop on the resistor, decreasing thereby the bias across the APD. This stops the avalanche. This image shows another example of a circuit that provides passive quenching. The avalanche is quenched by discharging capacitance following an avalanche. The passive components of the quenching circuit can be assembled either inside the APD package or can be added as a part of an external circuit. An important drawback of such passive quenching is slow recharge of the capacitor, which limits the dynamic range of the recorded optical signals. To increase the avalanche quenching rate, an active quenching is used. It allows to reduce parasitics, ensure faster quenching, increase sampling rates, and reduce after pulsing. However, the drawback of active quenching is larger real estate required for each single spot. Performance achieved for silicon spots is the following. Breakdown voltage below 30 volts, photon detection efficiency around 30 to 70% for up to 800 nanometer spectral range, dark count rate below 10 to power 4 counts per second at room temperature, time resolution less than 1 nanosecond, and gain is over 10 to power 7. Performance achieved for in-gas spots is about 10 times worse than that for silicon spots. It always looked very attractive to build an array of Geiger mode APDs. While designing arrays using separate APD chips was successful, such arrays had at least one serious drawback related to rather large real estate consumed by the quenching control circuits. Placing an array of Geiger mode APDs on a single chip had immediately revealed the other problem: optical crosstalk between the elements of the array that made such arrays useless. The origin of this crosstalk is radiating transitions of avalanche electrons between sublevels in the conduction band. One can easily see such radiation under the microscope in the dark room. Biasing a single silicon APD at or slightly above the breakdown voltage, we can observe whitish bursts of light in the microscope. Of course, we have to limit the APD current when doing such experiment. In the array of Geiger mode APDs built built on a single chip. A single burst within a cell of the array triggers the avalanche in all surrounding cells, blocking thereby the whole array from detecting the signal of interest. These problems were successfully solved in the device that was called silicon photomultiplier, also known as micropixel photon counter, and we'll discuss it next. Silicon photomultiplier is a multi-pixel array of APDs operating in a Geiger mode. The array may consist of tens of thousands of pixels with the active area size of down to 10 microns each. CPM are not just a simple two-dimensional array of Geiger mode APDs. These devices are designed on a single silicon chip. Each element of the array maximizes the fill factor, and the quenching resistor for each microcell is fabricated on the same chip right next to the cell's active area, which is shown schematically on the image. To eliminate optical crosstalk, the design features trenches between micropixels, which block optical quanta generated due to intra-valley radiative transitions of avalanche electrons. Without trenches, the optical crosstalk would fire neighbor cells, preventing any useful operation of silicon photomultiplier. The sources of noise in silicon photomultiplier include dark current avalanche, after pulsing due to trapping the releasing of carriers in avalanche region, electron tunneling effects, and optical crosstalk initiated firing, which can be eliminated or at least greatly suppressed. In a typical silicon photomultiplier, all microcells are connected in parallel. Each microcell includes the avalanche quenching resistor connected in series with the microcell. The output signal of CPM is a sum of outputs from individual microcells. Let's assume that we illuminate the array with a uniform beam of light that covers the entire array. Assume first that the beam consists of only a single photon in a short period of time. As we remember from quantum physics, this single photon can fire any microcell of the array with about the same probability. It means that the array response to a single impinging photon will be a brief spike of current with a high amplitude generated in a single random microcell. If two photons arrive simultaneously, they will fire randomly two microcells, and the output current will be with a twice larger amplitude. In a similar fashion, three photons arriving simultaneously will fire three different microcells, creating the output current 3 times larger than the signal from a single photon. If the incoming optical flux contains 3 photons arriving at different times, then the output current will have 3 peaks spaced in time accordingly. By accumulating total charge collected at the output of silicon photomultiplier during a short period of time, one can calculate the total number of output quanta arrived at the detector. The photoelectron spectrum of impinging light can be measured with a charge amplifier coupled to an analog digital converter, and it shows well-resolved peaks. A typical spectrum is shown on this slide. The first peak should be attributed to firing of microcells by dark electrons. This is a noise flow. The fourth peak has the highest amplitude, meaning that most of the microcells were fired 4 times during the integration period, which in turn means that 3 photons plus 1 dark electron arriving at a time was the most probable event. The performance achieved by silicon photomultipliers is listed on the slide to the right. The fill factor of 50 to 80% means that more than half of silicon chip is sensitive to light. The number of pixels per detector determines the dynamic range of silicon photomultiplier. The device will be saturated if the number of photons arriving simultaneously approaches or exceeds the total number of micropixels. The dark count rate of less than 10 to the power of 5 counts per second per square millimeter is of course very small, allowing detection of single photons during a brief period of time. And the pixel recovery time of about 20 nanoseconds is very, very good, allowing secure detection of nanosecond duration optical pulses. Well, this concludes my presentation. Thank you very much for your attention and for attending this presentation.
Thank you very much, Olex. We now have time for plenty of questions here. We already have a big list, so I'm going to go ahead and start. You described the structures to improve UV sensitivity of silicone APDs. What about the structures to improve IR sensitivity of silicone APDs?
Well, that's a question of life. So how to improve IR sensitivity? Many scientists and engineers are working on improving IR sensitivity of silicon, for example, silicon APD, to allow, for example, high gain at wavelengths above 1000 nanometers. And unfortunately, up to now, the only way, the best way to do it is to still increase the thickness of silicon, which will require, of course, applying high reverse bias. So that's the only feasible and most practical way for now.
Thank you. How do you electrically bias the Geiger mode APD to achieve single photon counting?
Actually, in the same way as we usually bias regular analog mode APD. So we can, for example, if the noise dark current rate of the APD that is supposed to work in Geiger mode is pretty high, and you're afraid of triggering the Geiger mode APD prior the required optical signal arrives, you can bias the APD using in a pulsed mode. You can apply high reverse bias, which exceeds the breakdown voltage within the small period of time when the optical signal is supposed to arrive. In this way, you reduce greatly the average dark count rate, and increase greatly the probability that the optical quanta will be detected by the Geiger mode APD.
All right, thank you. Attendees, just a reminder, if you want to ask a question, you can just type it into the box on the side of your screen. All right, our next question, could APDs be built thick enough to detect X-rays directly, i.e. thickness of less than 1 millimeter?
Well, it's a good question, you know. It could, but it's a question again about the applied bias, because you have to apply a certain reverse bias to create higher electric field that initiates the avalanche. And you know, assuming that we need about 1 millimeter thickness of silicon, well, it's possible, of course, but then you have to apply really good beveling, for example, of edges to sustain high reverse bias that supports avalanche in this kind of application. Frankly, I myself did not build this kind of APDs working for X-rays. I built many other types of APDs, but not anything like that.
Why in APDs is the bias voltage much higher than SAPDs? Although SAPDs are to be biased in Geiger mode, which goes beyond breakdown voltage. Which APD is biased?
You know, it just for solely by practical due to practical reasons, because the regular analog APDs, they are supposed to work in an analog mode. We do not want a regular analog mode APD to go into digital mode operation. We want to record signals with as high as possible dynamic range, and the signal has to be linear with light intensity. This is possible only when we create pretty uniform and pretty thick avalanche layer, and to deplete this layer completely and to create an avalanche condition, you have to apply high enough bias. In contrast, with Geiger mode APD, you do not care about excess noise. Absolutely. The only way you care is to create a condition when the avalanche could be started with very high multiplication with very high avalanche gain. It means that the only thing we need to care of is decreasing of the dark count rate and then bringing the operating point slightly above breakdown voltage when any electron or hole that arrives in avalanche region creates a huge avalanche with the gain of above 10 to power 6. It means that this could be created practically with very low operating bias, like below 30 volts.
Thank you. Is the gain bandwidth different for 2.5 APD versus a silicon germanium versus a silicon APD?
Well, you know, actually, it's not very different. Again, it depends on many parameters, structural parameters of APDs, and even different silicon or silicon germanium APDs may provide different numbers. So I would say that it's not much different.
All right. What measures should be taken to protect a 3.5 APD against ultra-short high-peak power pulses?
Well, it's actually the same measures that for any other APD. If I correctly understand the question, probably we are talking about blocking, preventing high current output currents from APD when large intensity optical flux arrives, right? So it's for as for any APD, we have to apply some quenching circuits, and the best way to do it is either to use, for example, passive quenching with a quenching resistor connected in series with the photodiode, or in many cases, when people are measuring light within the large dynamic range, it's very practical to use to bias the APD in a pulsed mode when you apply the reverse bias only when you expect the optical quanta to arrive. In this case, arrived optical quanta will be measured, but will not have enough time to burn or to damage the APD.
For Geiger mode APDs, is there any advantage in performance for the structures designed specifically for the Geiger mode operation in comparison with those structures that may work equally well in the analog and digital mode?
Actually, there is no real advantage. So if the APD that may work perfectly well in both modes, the analog mode and the Geiger mode operation mode, it means that when the dark current rate is low, in this case, you know, there is absolutely no advantage for the APD that was specifically designed to work in Geiger mode operation. Well, but of course, when you design the Geiger mode APD, so you have an advantage of not taking into account some structural elements and features and design and recipes of manufacturing that are very important for the analog mode APD. This simplifies manufacturing of Geiger mode APD.
All right, thank you. I'm going to take one more question here. What is the best BV range for high performance SAPD operation?
Oh, the lower reverse bias, the better, because all of us we care about the noise, and noise is lower for the lower operating bias.
All right, thank you very much, Olex. So that's all the questions we're going to get to right now, but anything we didn't answer today will be answered in a follow-up email. Also, this is being recorded. Everyone will receive a link to that, and if you'd like a copy of the slides, please contact me, the moderator, or Dr. Gusha. I'm going to close the webinar now. I would like to thank our presenter one last time, Dr. Olex Gusha, lead scientist for semiconductor devices at OSI Optoelectronics, and everyone who joined us today for Avalanche Photodiodes, Design and Applications, hosted by Photonics Media. Goodbye, everybody.